This video will cover section 9.4, which talks about two comparison tests. The first being the limit comparison test, and the next being the direct comparison test. So as these names imply, you will be comparing the series that you want to figure out whether they're converging or diverging with series that you know already the convergence or divergence of. So often a given series is going to closely resemble a p-series or a geometric series. So the first one we're going to cover is the limit comparison test, which is what occurs more often. So suppose that you have two series and their nth term is going to be greater than 0. So all the terms are going to be positive. And then if you take the limit, so this is why it's called the limit comparison test, as n approaches infinity of your two series, the ratio of your two series, and that equals a finite number that's also positive, then the two series either both converge or diverge. Now, A sub n is the given series. That's the series that you want to tell whether it converges or diverges. And then B sub n is your comparison series. So looking at number 1, we want to show that this series 1 over n plus 1 diverges. So if you notice, we want to come up with a series, like I said, most often a p-series or geometric series, that this series closely resembles the series 1 over n. So the only difference is 1 over n plus 1. So as n approaches infinity, there's really not much difference between 1 over n plus 1 and 1 over n. But you have to use the correct test in order to prove that it diverges. So we're going to compare this. So the first thing that you want to do is list out your comparison series. So we're going to compare this to the series 1 over n. Okay, so that's definitely something that you're going to have to write out to show what you're comparing to. Then, whatever you're comparing to, you need to know the convergence or divergence of that. So next, you would kind of prove the convergence or divergence, just like we've done in the past. So 1 over n, remember, was a p-series, but it was a special p-series called the harmonic series. So if it's harmonic, 1 over n, you don't even have to really prove anything. You just have to state that this is harmonic, therefore it's divergent. Okay, so what we want to do now, since that comparison series, that's our b sub n, so now we want to take the limit as n approaches infinity of the ratio of 1 over n plus 1 divided by 1 over n. So that's what I'm going to write out next. Okay, the limit as n approaches infinity of 1 over n plus 1 divided by 1 over n. Now, I typically don't write this first step because a lot of times our series are fractions. And so if you're finding the ratio of two fractions, what step I typically go straight to is, oh, I didn't even write that down. Hold on. Okay, this is what I would normally write down is, instead of writing it as a ratio with the fractions, I would write the first series and then times the reciprocal of the convergent series. Now for this first one, this is quite simple, so you did not necessarily have to do that, but you'll get to more complicated ones where it's going to be valuable to do that. Alright, so then when we simplify that, we get n over n plus 1. And then the limit as n approaches infinity. You don't have to do L'Hopital's rule since this is a rational function. You can just say the same name. So that equals 1. Now, remember, this is not the nth term test. This is the limit comparison test, which says that if the limit is finite and positive, then the two series are going to both do the same thing. So since this does equal 1, which is finite and positive, then this series does whatever our comparison series does. Therefore, it diverges. And you want to state the test that it diverges by, which is the limit comparison test. Now notice here, I made it shorthand, LCT. The AP test does recognize LCT as the limit comparison test. You don't want to shorthand a lot of things, but this one you can, it is recognized. Okay, so that's how the limit comparison series works. So as I said, this one's pretty basic, but sometimes it can get a little bit more challenging or just a little bit more complicated in how you compare the series. So number 2, we're not actually going to prove the convergence or divergence of these series. We're just going to talk about what you would compare the series to. So for the first one you see there, you have 1 over 3n squared minus 4n plus 5. So the comparison series, you would go with the highest degree. So I would compare this to the series 1 over n squared. All right, and so this is a p-series where p is equal to 2, which is greater than 1, therefore this is a convergent p-series. So if we were to do the limit comparison test, then most likely we would get that this converges. Now, one thing I want to mention really quickly is what if you don't get a finite number? What if you do the limit comparison test and you don't get a finite or positive number? Then what that means is the limit comparison test would have failed. Then it would be inconclusive. So if that were the case, it doesn't happen very often with limit comparison tests. It either means that you compared it to the wrong thing, so you might go back and try comparing it to something different. All right, so then the next series that we compare, we have 1 over the square root of 3n minus 2. So the degree here in the denominator would be 1/2. So we would compare this to the series 1 over n to the 1/2, which again is a p-series, but p is equal to 1/2, less than 1, therefore divergent. Now, the last one is a little bit different. This is something that we can use the comparison test with, but in order to compare this, you have n squared in the numerator into the fifth in the denominator. Now, if we want a p-series, we can only have our n to the exponent in the denominator. So what you have to do is you look at the degree in the top and the degree in the bottom, and you simply apply those exponent rules there, and so that would end up being n cubed in the denominator if you subtract. So we're going to, for this one, compare to 1 over n cubed. So again, 5 minus 2 is 3, so we can compare this to 1 over n cubed, which is a p-series where p is greater than 1, therefore it converges. Okay, so we're going to get some more examples with this that are a little bit more challenging and different than the first one. Okay, so number 3. We have the series square root of n over n squared plus 1. So think about what you want to compare that to. In the numerator, you have the power 1/2. In the denominator, you have the power of 2. So if you were to apply your exponent rules there, 2 minus 1/2 is 3/2 in the denominator. So we're going to compare to 1 over n to the 3/2. So again, you have to make this statement before you can apply the limit comparison test. So we're going to compare it, and then you also have to prove the convergence or divergence of that. So this is a p-series, and this is another way of writing the statement. You can say it's a convergent p-series where p is equal to 3/2, which is greater than 1. So there's lots of different ways you can write that statement, just as long as you have those 3 essential things, whether it converges or diverges, why, so in this case it's a p-series, and then, or what kind of series, sorry, and then the why. Okay? All right, so if we're going to compare this, so remember the limit comparison test says that we're taking the limit of our series divided by the comparison series. So as I said before, most of these series are fractions, not all, but most of them are fractions. So what I'm going to do is I'm going to go straight to the limit as n approaches infinity of the series I have times the reciprocal of the comparison series. Alright, so with that, then we're going to simplify. So we have n to the 1/2 in the numerator. So if we multiply like bases, n to the 1/2 times n to the 3/2, then we'll get n squared in the numerator over n squared plus 1 in the denominator. Again, this is nice and neat. This is same name again, so we get a finite number of 1. Therefore, it's going to do whatever the comparison series is doing. So the comparison series is convergent, therefore this series is convergent by the limit comparison test. Alright, number 4. So number 4 is a little bit different. As you can see, all the other examples that we did, number 1, number 2, and number 3, all of them were just regular n to the power of. But this one here, we have the n's to the power of 1 in the numerator, n to the power of 3 in the denominator. But then we have this nice little exponent here of 2 to the nth, which kind of throws things off a little bit. If the 2 to the nth was not there, then this would just be, just like the other ones that we compared, we would compare this to 1 over n squared. But that 2 to the n throws a wrench in things, and we can't just ignore it. So what I'm going to do is I'm going to leave the 2 to the n in the numerator, and then I'm going to simplify the degree to n squared in the denominator. So I'm going to compare to this series here. And actually, that was a typo there. That should have been 2 to the n in the numerator over n squared. Now, this one is neither a geometric nor a p-series, so we have to come up with a different way of proving the convergence or divergence. But this is much simpler, 2 to the n over n squared, than this series over here. So what I'm going to try first is I'm going to try the nth term test. So remember, the nth term test says the limit as n approaches infinity of a sub n. If that approaches anything but 0, then it's going to be divergent. And this seems divergent to me because 2 to the nth exponential is going to grow much, much faster than n squared. So it would seem as if this would approach infinity, but you have to prove it. So, and that's going to apply L'Hopital's rule. So a couple of steps, actually. So if we apply L'Hopital's rule, you take the derivative. So why we approach L'Hopital's rule is because we have infinity over infinity. So we take the derivative of the numerator and the denominator. Now recall that the derivative of an exponential function would be natural log of whatever a is, which this is 2, times the same thing, 2 to the n, divided by the derivative of n squared is 2n. Then when you evaluate as n approaches infinity, you get infinity over infinity again. So apply L'Hopital's again, and you get natural log of 2 squared times 2 to the n divided by 2. Now if you plug in infinity, you will get infinity over 2, which is infinity, which is not equal to 0. Therefore, this is divergent by the nth term test. Okay? So anytime you do a comparison series, it's kind of like you're doing two problems because you have to prove the convergence or divergence of the comparison series and then use that to prove the convergence or divergence of the series you actually are wanting. All right, so this is divergent, so we're going to apply the limit comparison test and see if our actual series is divergent as well. So limit comparison test, we're going to take the limit as n approaches infinity of our original series times the reciprocal of our comparison series, n squared over 2 to the n. Now, notice when this happens, you have the 2 to the n over 2 to the n, and this is why I go straight to writing the reciprocal, because a lot of times things will cancel out like this. So the 2 to the n's cancel out, and then when you simplify, you get the limit as n approaches infinity of n cubed over 4n cubed plus 1. Again, it turns out nice and neat for us as same name, so this is equal to 1/4, which is finite and positive. Therefore, it's going to do what our comparison series did, which is diverge by the limit comparison test. Okay, so that's the limit comparison test. That one is going to work and be used most of the time. But there is another test that's a comparison test that we need to make sure and understand, and that is the direct comparison test. Okay, so the limit comparison test, as it says in the name, it's comparing and you're taking a limit. The direct comparison test is not going to involve a limit. It's directly comparing the series to a comparison series. So what this states, now I don't really like the way this talks about the direct comparison test. This is coming out of the book, and this is how the book describes the direct comparison test, which can be quite confusing. So off to the side, I'm going to kind of put my version of things for the direct comparison test, which I find a lot simpler. So if your comparison series is divergent, then you want to prove that the original series is bigger than the comparison. Okay, so what we're looking at, and as you can see, it has this inequality here. So all you would do is, if the comparison series is divergent, then if you can prove that the original series is bigger than that, that means approaching a bigger number, then you would also prove that the original series is divergent, if you can prove that it's bigger than the comparison series. Okay? Then vice versa is true. If the comparison series is convergent, then you would want to prove, so if you know that the comparison series is convergent, that is the sum is approaching a finite number, then if you can prove that the original series is smaller than the comparison series, then you can prove that the comparison series is also convergent. Because if you prove that the original series is bigger than a convergent series, then it could converge or diverge. We don't know. Okay, so I like to use kind of this reasoning a little bit better than what is off to the left, which is a little bit harder to decipher. Okay, so let's see how this works. So determine the convergence or divergence of the series sine of n over n squared. Now, notice that for this one, you have to have the series, or the nth term, be greater than 0. And if you think about sine of n, that's going to be oscillating between -1 and 1. So sine of n is not necessarily greater than 0. And to apply the direct comparison test, we have to have that be the case. Now, this example is here because we can still do it. But what we're going to have to do is we're going to have to look at the absolute value of sine of n. Because if we look at the absolute value of sine of n, then this series is going to be greater than 0. Now, the reason I can do that, and this is something that I haven't gone over yet, but I'm just going to quickly type it here, and then we're going to look at it more in depth later. But if the absolute value of the series is convergent, then it follows that all the time, if the absolute value of the series is convergent, then the original series is convergent. Okay, so knowing that, and like I said, this is just kind of a little aside that will go into more depth in a later video that we're going to apply here. Okay, so the absolute value of sine n is what I'm going to look at and prove that that's convergent, and therefore the original one would be convergent. Okay, so we still need to compare this. Now, sine of n we know is going to oscillate between -1 and 1, and the absolute value of sine n will be no bigger than 1. So what I'm going to actually compare this to is I'm going to pretend that the numerator is going to be 1, right, because it'll get no bigger than 1, and then the denominator would be n squared. So I'm going to compare to the series 1 over n squared, which is a convergent p-series where p is greater than 1. Alright, so since this is convergent, then I'm going to say if the comparison series is convergent, then prove that the original series is smaller than the comparison. So what that is I want to prove that this absolute value of sine n over n squared plus 1 is less than or equal to, it can be equal to as well, 1 over n squared. So I'm going to write this statement here. So in this one, I put 1 over n squared is greater than absolute value of sine n over n squared plus 1, which is fine as well. Now, when you solve inequalities like this, you always have to go the top left times the bottom right, and that needs to go on the left. So if you use these arrows here, then so the bottom right to the top left is going to go on the left, and then the bottom left to the top right is going to go on the right. So we have n squared plus 1 is greater than or equal to n squared times the absolute value of sine n. Now, absolute value of sine n, remember, it's going to be no larger than 1. And then, other than that, it will be a fraction. It will be less than 1 between 0 and 1. So that's times n squared will, in fact, be less than or equal to n squared plus 1. Therefore, the series converges by the direct comparison test. Now, I've had people in the past ask me about this because couldn't you have intuitively figured that out from the first line? 1 over n squared being greater than or equal to sine n over n squared plus 1. Yes and no. Yes, because obviously you can tell that 1 over n squared is greater than or equal to that. But I would take it one step further just to show, just to be absolutely sure and just to show that a little bit more. So I would take it down after you cross multiply, and then this is pretty clear. You don't have to take it much farther than that, that this statement is true. Then you can say, therefore, the series converges by the direct comparison test. Okay? All right, so we're actually going to do one more. We're not going to do the final one. We'll do that in class. So for number 2, we have 1 over 2 plus 3 to the n. Now, in most all the other examples, we've compared to p-series, but this one's actually going to be geometric. What we're going to compare this to is 1 over 3 to the n, which then we would compare that to 1/3 to the n. which is a geometric series where r is equal to 1/3, therefore less than 1, so it's convergent. So again, if we have a convergent series with a direct comparison test, we want to prove that this statement is smaller than 1 over 3 to the n, or 1 over 3 to the n is greater than 1 over 2 plus 3 to the n. Okay, so then if we, again, cross multiply, we have 2 plus 3 to the n is greater than or equal to 3 to the n. That's pretty obvious. Therefore, we can state that this is a convergent series by the direct comparison test. Okay, so that's it. That's limit comparison test and direct comparison test. Limit comparison test, like I said, tends to be seen more often and is going to work pretty much all the time. Direct comparison test can be a little dicey, and so we're going to see that with example 3 in class and see how to deal with that when the direct comparison test doesn't always work. But you do need to know both. Both will be tested on the AP test.